All right, good afternoon, everyone on the East Coast, or good morning, good evening, depending on where you are in the world. My name is Sarah Lastbeach. I'm really excited to be hosting session 209, Statistical Innovations for Error-Prone Data. Our first speaker, we're going to flip up the order from the program. They're both great, stay for both, will be Dr. Donna Spiegelman from Yale University in the US. So I'll stop sharing my screen, Donna, let you share yours, and take it away.
I'm just adjusting, getting to a slideshow from the beginning. Okay. Hello, everybody. There's a comment in the chat, and I guess, Sarah, you can maybe monitor that. But hello, everybody. I want to thank Sarah Lostbeach very much for inviting me to speak at this conference today. And it's a pleasure to be participating in the International Day of Women in Statistics and Data Science. And I'm so happy to see that such an event is being organized and has been in existence for several years. Here is who I am. And I guess the most important things are I'm a professor of biostatistics, and I'm the director of our Center for Methods and Implementation and Prevention Science at the Yale School of Public Health. And I'm also a professor emerita of epidemiology, biostatistics, nutrition, and global health at the Harvard School of Public Health. And what I'm going to talk about today is a talk titled The Limits of Confounding the Boundlessness of Measurement Error. And so here graphically we see confounding constrained very much in a tight cage, and then measurement error breaking free of the cage and flying free and boundlessly in the sky. And what do I mean by this? What I mean is I'm talking about how there's a very strong interest these days in causal inference in epidemiology and clinical research and biomedical research and public health research. And in order to make causal inferences, we have to remove bias from our usual methods of estimation and inference. And in epidemiology, we've always thought that there's three major sources of bias: confounding, measurement error, and selection bias. And there's been a huge amount of attention to the reduction of confounding bias in epidemiologic and public health and clinical research. And basically, that's been the major focus of causal inference methods. Meanwhile, I have for many, many years, along with my co-speaker, Dr. Grace Yee, have focused a great deal of our career on developing methods to remove bias due to measurement error. I'll say a little bit about what each of these is. So confounding bias is caused when there's some sort of background variable that's associated with the exposure, treatment, or intervention of interest, and also with the outcome. And if we don't control for that variable in some way, we're going to attribute effects to our exposure of interest that are actually due to this background confounder. And the problem is that we don't necessarily know all the causes of outcomes and diseases that we're looking at. So we may not be able to measure and control for these confounders. And even when we do, we may measure them imperfectly and then also not be able to control for them well. And so causal inference methods try to deal with that. The major way, or the sort of gold standard or strongest way of dealing with both measured and unmeasured confounding is to randomize studies. And by randomizing, we balance the treatment groups with respect to these various background variables, whether we know what they are or we don't know what they are. And so though their effects will sort of cancel out, in the end, we can get an unbiased estimate and make causal inferences. But of course, there's many, many exposures and treatments and interventions of interest that we're not able to randomize. And so that's when we get into the causal inference methods. So that is, to bracket, the confounding piece. And then measurement error is another source of bias. when we randomize, we almost always know which is the treatment group and which is the control group. So we don't have that problem either. But otherwise, in observational research where we haven't randomized or assigned the treatment or intervention group, we have to worry about measurement error and that exposure, and then also possibly in the confounders as well. And so I'm going to argue in this talk that the major source of bias, despite the big focus on causal inference methods on reduction of bias due to confounding, is actually the major source of bias is measurement error. And then, of course, encourage you all to maybe focus more directly on the development of measurement error methods. There's still a lot more that can be done. And then also to utilize the methods that already exist, of which there are many, many good methods developed by myself and others I've worked with, by Dr. Yee, our second speaker, and many others. So the question is, to what extent can an estimated exposure disease associated be explained by residual and unmeasured confounding? And one way that question is answered and quantified is by the E-value. And that was laid out in a paper in 2017 in the Journal of the Annals of Internal Medicine by Vanderweel and Ding. And Vanderweel is a leading causal inference methodologist. And so what we have here is for an observed risk ratio, and so the notation is RR observed, ED, and there are two background quantities, the relative risk for the outcome in relation to the confounder U, and then the probability of the exposure U given U equals 1 over the same value when U equals 0, which quantifies the magnitude of the confounder exposure association. So Vanderweel and Ding derived this a relatively simple expression called the E-value. That's a function of these two quantities, and basically says that in order for an observed association to be due to confounding, it must be that the product of the outcome confounder association times the confounder exposure association must be greater than this E-value. And that's the number here. And then a little more refined version of this formula was derived here. So for an observed association, we can calculate this formula and then see how big this product has to be in order to explain this observed association. So it's very easy to calculate and applies very generally to all sorts of models, outcomes, and exposures. So the first point here is, again, to emphasize that the extent to which confounding bias can explain an observed association has these relatively tight and known bounds. But actually, the bounds are even tighter. The E-value is an underestimate of what those bounds are. And what the bounds actually are, their exact values rather than this approximate bound, was developed initially in a paper in 1959 by Cornfield. And very interestingly, the history of that has to do with the debate that occurred about whether cigarette smoking caused lung cancer. And it was denied by the tobacco industry at that time that cigarette smoking did cause lung cancer. And rather, it was claimed that the association that we were seeing between cigarette smoking and lung cancer, where there was a relative risk of around 10 of heavy smokers having a 10 times higher risk of lung cancer than non-smokers, was caused by unmeasured confounding by other variables. So Cornfield derived these bounds similar to the E-value, and then these were further refined by Bruss in 1965, by Schlesselman in 1978, and others. And again, trying to represent the minimum strength of the association on the risk ratio scale that an unmeasured confounder would have to have with the exposure outcome associate, conditional on the measured covariates to explain away the observed effect. So it's important to note that the e-value from this 2017 paper by Vanderweel and Ding assumes that the prevalence of the confounder is 50%, which is when confounding bias is at its maximum in general with respect to the bias it can cause. So because confounders usually have a prevalence less than 50% or greater than 50%, the e-value is an overestimate of the extent to which residual confounding can explain observed impact estimates. I think in the interest of time, I'm going to skip. I have some slides about healthy lifestyle as the unmeasured confounder. That was the culprit in looking at many observational studies examining the effects of diet, physical activity. Some of you may be aware there's been a very big controversy about the impact of postmenopausal hormone use in women, and even environmental exposures such as air pollution on health. And various actors have claimed that these associations that we've seen very repeatedly in observational studies are due to unmeasured and residual confounding by healthy lifestyle factors. So, I mean, I'll just say very quickly that we've looked at the extent to which healthy lifestyle is common in standard cohorts of even what might be considered healthy epidemiologic study participants, such as health professionals and nurses. And we found that in the health professionals follow-up study at Harvard, only 3% had no unhealthy lifestyle behaviors. So the prevalence of unhealthy lifestyle is 97%, and meaning that healthy lifestyle is 3%. And similarly, in the nurses' health study, the prevalence of healthy lifestyle was around 20%. So this is all to say that healthy lifestyle is actually a relatively rare confounder. So its impact in explaining observed associations is going to be even weaker than what's given by the e-value. So we can use Schlesselman's 1979 formula to look at it, and it has this form. So as I mentioned, the e-value is only a function of the relative risk for the outcome in relation to the confounder and the relative risk for the exposure of its association with the unmeasured confounder. But now we have to throw in the confounder prevalence, PU, and you see it here in multiple places in the formula. And then with my Yale PhD student, Ray Liu, we obtained the formula for the e-value plus. Well, that's the Schlesselman formula right here. And then we can compare that to the e-value plus when the prevalence is 0.5 using this expression, or we can compare the e-value plus to the e-value with this expression. And then we can create this plot. And what we're doing here is we're looking at the relationship between the e-value plus to the e-value, which says how much greater does the product of the unmeasured confounder have to be with the outcome times the association of the unmeasured confounder with the exposure in order to explain away the observed association, say of 1.35, which is what was seen in a meta-analysis of a large number of studies of diet in relation to cancer. And so we can see that the e-value is e-value plus is much higher than the e-value. Say if we're at a confounder prevalence of 0.2, which is the healthy lifestyle prevalence in the nurses health study, it's going to be limited if the confounder exposure association is 1.5. We can see that the e-value is going to be around maybe 9 or 10, but it does drop down if the associations are higher. Then it's smaller, but it still means we have to have associations still 5 times, possibly 3 to 4 to 5 times higher than we would have needed if we just used the e-value. and so on. So this is just to, again, emphasize quantitatively that the bounds on confounding as a cause of bias are actually quite tight and rather unrealistic, given that we're already in most observational studies controlling for all known risk factors for the outcome. So there's got to be other mysterious, very strong risk factors for the outcome that still haven't been discovered, and or such poor control for known risk factors that we still have substantial residual confounding. Again, unlikely. And if you're thinking genetics are these mysterious unmeasured confounders, many of you may know that maybe the past 20 years there's been, multiple millions of dollars spent searching the human genome for strong risk factors for common cancers, cardiovascular disease, diabetes, and so on. And really, nothing's been found. We don't seem to have these strong risk factors genetically either. So unlike confounding bias, which has the tight bounds, as I've discussed, bias due to measurement error has no bounds at all. So here is a table from a textbook, Principles of Exposure Measurement in Epidemiology, that was published in 1992. And what we have is, here is what the true odds ratio is. We're using a very simple measurement error model where we have the true exposure and we're just adding noise to it of various magnitudes determined by the correlation of the true exposure with the surrogate, the observed measurement, which is a sum of the true exposure plus the noise. And so when the correlation is 0.9, we could say measurement error is about 10% of the variation in the observed exposure. When it's 0.5, it's about 50%. 0.3, it's about 70%. And we can see that if the true odds ratio is 1.5, and about 50% of the variance of the observed exposure is due to noise, we'll observe an odds ratio of 1.22. If the odds ratio is 2, we'll observe a 1.41. If we observe a 4, it goes down to 2, and so on. And really, you can increase measurement error from 0.3, 0.2, 0.1, and you can see that the observed odds ratio can go to 1 even.
Sorry, Donna, but we're out of time.
Okay, so I will just summarize by saying I've shown that confounding bias is not likely to explain most of the associations that we observe in observational research, whereas measurement error can lead to bias towards the null of almost down to no effect at all. And our next speaker, Dr. Grace Yee, who is a international expert in methods to adjust for this bias and measurement error, will give us an illustration of some methods that have been developed to deal with what I consider to be the major source of bias in observational research. So thank you very much, and I'm very pleased to close up my talk and turn it over to my colleague.
Thank you so much. And go ahead and share your screen when you're ready, Grace.
So can you see it?
Yes, thank you so much.
Okay. So thank you, Sarah, for organizing this session and inviting me to speak here. And also thanks, Donna, for opening this with a very nice introduction on the importance of measurement error problems. So I'm going to talk about the zero-inflated Poisson model, which is a joint work with my former PhD student. So first, I'm going to quickly introduce the problem of our interest. In this project, we are particularly interested in zero-inflated count data, which typically for zeros, we classify them as structure zero or sampling errors. And we are interested in evaluating the situation when count data are subject to measurement errors, which could include undercounting or overcounting. So my goal here is trying to come up with meaningful measurement error models and also examine the measurement error effects and finally develop a valid inference procedure. And N represents a sample size, Y represents a count outcome, X represents related covariate vectors. And in this case, we differentiate at-risk or not at-risk groups according to their outcome information. So for at-risk group, we assume the measurement follows a Poisson distribution. Otherwise, not at-risk group will take outcomes to be zeros. So in this case, I use AI to represent a latent indicator for each group. And normally we don't know each unit status, whether or not it is at risk or not at risk group. But I use phi I indicate the probability, and mu I represents the average outcome for at risk group. So typically we have this setup. For not at risk group, we have 1 minus phi I probability to take value 0. Otherwise, outcome will follow a Poisson distribution with mean mu I. And usually we can use a regression model to link our outcome with covariates. So here beta represents a model parameter of our interest. And in reality, my yi may not be precisely measured. So here I'm going to use yi star to indicate the actual observed outcome. We call it surrogate. And in ideal situation, I want my observed outcome yi star and true outcome will be identical. But in reality, there would be errors. So here I'm going to use Zi plus and Zi minus to indicate two types of error, and on or and in or leave out error. I'm using coefficient C plus and C minus to indicate the type of mismeasurement. If both C equals 0, that means I have no measurement error. Otherwise, I may have either leave out or add in or both types of error. And also, we assume the error term Zi plus is independent of outcome if I know true covariates. So this is sort of like our ordinary use the non-differential measurement error mechanisms. And also we assume this error Zi plus follows a Poisson distribution to indicate its boundless. I should say it's boundless, not unboundless. And also we want to indicate the larger value will have a smaller probability. And for Zi minus error terms, I assume it is binomial distributed because for this leave out error Zi minus, it can't be bigger than the actual true value. So that's why we assume it is binomial distributed. And in this two measurement error process, we have two additional parameters, lambda I and pi I. So here we could treat them as a constant, or we might further model them in terms of some dependence on some like extra some additional covariates information, which is denoted by Wi plus or Wi minus. So here and high level, I just want to emphasize we have a measurement error process, which may involve additional parameter alpha. Our goal here is try to understand the inference beta, which is of our primary interest, but unfortunately we have to couple our inference procedure with dealing with nuisance parameter alpha here. So the next part is I'm trying to evaluate how my traditional analysis by ignoring measurement error feature might influence our analysis results. So the second part is trying to look at the surrogate variables influence on our models. Still assume my true y is a zero-inflated Poisson distributed. If I have C plus equals 0, but C minus equals 1, which means I only have leave out errors. It turned out my surrogate yi star will still follow the zero-inflated Poisson distribution, which is quite interesting. The only difference is its mean for non-zero part will be alternated in such a way, instead of being mu I, which is the original mean for my original model of yi, it will be reduced by a factor 1 minus pi I, which related to the measurement error degree. And if I look at the other situation, I only have add-in error without leave-out error, then the distribution for surrogate y star will not be zero-inflated Poisson distributed anymore, but instead it will be a mixture of two Poisson distributions with different means. And for more general situation, if I have two types of error, add-in error, leave-out error, then the surrogate variables yi will also follow a mixture distribution involving two types of Poisson distributions. And different from the previous scenarios, for the second part, my y tilde, its mean for Poisson distribution will not be mu I plus lambda I, but it will be reduced by including an additional factor 1 minus pi I, which is related to leave out measurement error process information. So finally, I'm going to look at the situation. How would this finding will affect our inference procedures? In other words, can I still use the observed surrogate yi to do inference for my original interesting parameter beta related to the relationship between yi and xi? So here, in ordinary situation, we do need information for my measurement error process. But unfortunately, in some situation or many situations, we don't have additional data to help us understand the measurement error degree. So in this case, to get around of these non-identifiability issues, we put ourselves in Bayesian framework by introducing some prior information to get around this non-identifiability issue. To do that, we do some reparameterizations for one parameter by introducing this theta 1. And then we examine our posterior distributions. And here quickly, I want to introduce prior. And for prior, we may have a proper or improper prior. So for proper prior, I require its integral will be finite, and which will give me proper posterior. So if I apply this context to our setup, then we find the conditional distribution after reparameterizations will be free of one particular parameter beta mu 0, which is related to the intercept of my primary models. And it turned out, depending on my prior pi theta is proper or not, then posterior distribution could be proper or improper. So for part C, we found if I have an improper prior, I can still make my posterior to be proper if and only if the following two condition is satisfied. Posterior for theta 1, theta 2 would be proper, and the prior for my intercept mu beta mu 0 is proper. So this basically give us some information that when I do inference, this gives me certain guarantee to ensure my posterior distribution could be properly specified. So since I don't have time, I only mention we also develop a data augmentation approach for inference by putting us in Bayesian inference framework by introducing prior distributions. So here I'm going to conclude my talk by quickly show you an application to prostate cancer studies. In this data set, we have two subsets coming from different sources, including different number of subjects, and we consider 4 different marginal analysis by focusing on one of the 4 pathways. We are particularly interested in evaluating the relationship between the level of mutation and the tumor stage. So here, X represents tumor stage information and Y represents count of genes. And we consider 2 approaches, incorporating possible measurement error issues and ignoring that. So the graphs compares the results. So the green intervals represent the proposed method, and the black intervals represent the traditional approaches. So it turned out And tumor stage T3 plus, patients do not have a mutation difference from those at T2 stage. And in terms of the intercept term, we found for the three pathway, MAPK, CCR, and EC, prostate cancer patients have more mutations in those pathways than patients in P53. So I'm going to wrap this up. In this talk, we particularly look at zero-inflated Poisson models. And we know these are very useful in applications, especially like for genomics studies, but traditional analysis could be challenged by the presence of measurement error. So in this project, we come up with a new measurement error models trying to incorporate different natures of measurement error. Could be counting down, like undercounting or overcounting by introducing two different error terms. And we also examine the measurement error effects and come up with a valid inference procedures by putting ourselves in Bayesian framework, because in this motivating data set, we don't have validation or repeated measurements to help us understand the degree of measurement error. So then we use the introducing prior information or assumptions to get around the identifiability issue. So this is all my project about. Thank you very much.
Thank you both so much for two great talks. I'm gonna pass the room over to our next session, but thank you so much for your time and really cool insights.